Jnanam paramam dheyam. Knowledge is supreme.
Welcome back. We have now seen what do we mean by frequency domain analysis, and that what we do is we capture what is known as the frequency response of a system. That is, we compute what is amplitude ratio and phase, what is the variation of amplitude ratio and phase with respect to frequency, and we have seen that it can be represented as a Bode diagram or an Nyquist diagram. So, let us now see how do we use this information to compute or to assess the stability of a feedback system. So, we will see stability assessment of feedback system in frequency domain. So, in order to do that, we will consider one thought experiment, so that it will help us kind of understand what are the stability conditions when we do the stability analysis in frequency domain, and there are, in fact, we are going to see two stability criteria, and both these are sort of evident from this simple thought experiment. So, let us consider an imaginary experiment of a feedback system. So, let us start with a feedback system. This is our process GP. This is the disturbance transfer function. This gives you output Y. Then you have a measurement. Then you have this measured output. If we go back from here, you have the wall transfer function. Before that, we have the controller transfer function. And this is error, and error is the difference between the measured value and the set value. So, I have deliberately not shown this particular link because in this thought experiment what we are going to consider is that we are going to see we are going to inject sinusoidal input here. So, we are going to say the set point trajectory is a sinusoid input. So, let us say this is a sine omega t. We are going to input a sinusoid here, that kind of brings in why we are in the frequency domain, and then accordingly we monitor how does Ym look like. So, and in the sort of, even though we are assessing the stability of a feedback system, the analysis or the thought experiment actually starts with the open loop, that we have opened this loop. We are not going to feedback the measured value, we are just going to assess the feedback value. So, if you see what we have is in this case the error is y set minus Ym. Here Ym is not supplied, so let us consider it to be 0, which is equal to a sine omega t. So, your error is a sine omega t, and if you look at what is the transfer function between Ym and epsilon s, it is, if you have to go from epsilon to Ym, it is Gc times Gv times Gp times Gm, and this is also represented called as GOL. So, it is called as an open loop transfer function between the measured output and the error, which is the product of these four transfer functions, and we are going to give a sinusoidal input here as y set, but it is going to be equal to epsilon because Ym is 0. And as there are these four processes, depending on these four transfer functions, we will see the output Ym will again be a sinusoid. So, even though I am saying we want to monitor Ym, it is going to be a sinusoid with a certain phase. So, it will have a certain phase and it will have a certain amplitude ratio. So, this will be amplitude ratio times A because if this is A. So, we have already seen how do we compute these two. So, we know that if this is the input sinusoid and we are interested in finding the output, then this AR and phi would be obtained by using the frequency response of this particular transfer function, which is the product of these 4 transfer functions. So, depending on the frequency, these phase as well as amplitude ratios would change. So, in this particular system, let us try to see that consider a frequency. So, we will consider a frequency omega such that the corresponding phase is minus pi or minus 180 degrees. So, in that case, if I say Ym will be equal to whatever is the amplitude ratio times A into sine of omega t plus phi omega t minus pi. So, it is going to be equal to minus A times AR sine of omega t. So, what we are seeing is, so this Ym is inverted form of y set because it is minus and we have some magnification or reduction in terms of amplitude, but if you look at overall signal the y, so this is equal to y set. So, this is actually AR minus AR times y set. That is why I said it is inverted, because there is a minus sign, there is a gain of AR, or otherwise it looks very much like y set. So, now coming back to our thought experiment, now let us see that we have this particular frequency omega at which phase is minus pi. So, that this is minus of AR times y set, and at that whenever you have that, we have found that frequency, you now close the loop. So, at that particular point we are going to close the loop and we are going to make it 0. So, what we are going to do is we are going to close the loop and y set goes to 0. Now, let us look at what would be the error. Error is still y set minus ym. So, now y set is 0 and ym we have just calculated as minus a AR sine of omega t. So, this is equal to a times AR sine of omega t. So, you can see that earlier our error was a sine omega t. Now, it looks very similar to that, even though the set point is not there, we have still have error is a sine omega t, which is multiplied by AR. So, let us consider that if AR is equal to 1, then epsilon t is equal to a sine omega t. So, you see that epsilon is a sine omega t, which is same as what we had put in earlier. So, that means before closing the loop, the system was oscillating at a sine omega with this frequency, and the moment I close the loop, and even though there is no set point change. So, when I say y set equal to 0, all these are deviation variables. So, that means the system is not subjected to any external conditioning, and still this epsilon is equal to a sine omega t. It will go through all these transfer functions, and what comes out is still a sine omega t, and then the system will keep on oscillating at a sine omega t. So, the implication of this is that even though y set is equal to 0, system continues to oscillate or sustained oscillation, even though the original source of the oscillation is gone. So that means if I have phase of minus pi and if the corresponding amplitude ratio is 1, then I am going to get sustained oscillations. So what are the results out of, so results from the thought experiment? If phase is equal to minus pi and corresponding AR equal to 1, we get sustained oscillations. And if you recall from the previous definitions of stability, this is as good as marginal stability, and it typically represents the limit of stability. Now let us consider if for the same phi equal to pi, AR is greater than 1. So we go back to this same figure. We have closed, before closing the loop, we know that this Ym or this recirculating error is going to be A times AR sin of omega t. So what does that mean? We closed the loop, we made the y set to be 0, and if AR is greater than 1, if I put in A sin omega t, what I get is something which is more than A sin omega t. Then that goes into this next cycle, what we will get is even higher than that. So every successive cycle amplitude grows. Because you will get AR raised to n. So the amplitude will keep on becoming AR raised to n. So what does that mean? The system is unstable, because the system will have growing oscillations. And similarly, you can also show that if for the corresponding case AR was less than 1, in that case every successive oscillation would have a smaller magnitude. So oscillations diminish, and what you have is a stable system. So simply by looking at what happens when your phase is minus pi, through this thought experiment we can make a claim that if at this particular frequency, if amplitude ratio is 1, the system has a stability limit, is at the stability limit. If that corresponding amplitude ratio is greater than 1, the closed loop system is unstable, and if that if that corresponding amplitude ratio is less than 1, then you have an unstable, when you have a stable system. So what all we need to do is, in order to assess the stability, you start with the open loop transfer function, which is Gp, Gv, Gc, Gm. Then you compute its amplitude ratio and phi, which is the amplitude of GOL and angle of GOL. Then you compute omega equal to what we call as a crossover frequency. Such that phi of omega crossover is equal to minus pi, and then you compute AR at omega crossover. If it is equal to 1, you get sustained oscillation or marginal stability. If it is less than 1, it is stable. If it is greater than 1, unstable. So, this principle we will be using in order to formulate two stability criteria in frequency domain. The first of which is known as body stability criteria. So, which is presented here. So, you can see that in the body's stability criteria, it starts with an assumption that if AR with amplitude ratio and phi are the monotonous functions of frequency, which are typically most of the cases most of the times is the case, the feedback system is unstable if the amplitude ratio at the crossover frequency, which is when phase is equal to minus pi or minus 180 degree, is greater than 1. So, that is the body stability criteria, and in order to compute that we need this GOL, which is GP, GV, GC and GM. So, it follows directly from the thought experiment that you compute the frequency at which at which phi is minus pi, and compute the corresponding amplitude ratio. If it is greater than 1, system is unstable. If it is less than 1, it will be stable. So, here it is represented as a body diagram for a stable system. You can see that at this particular frequency, you would see that the phase is minus pi, and then you move up into the first figure, you compute what is the corresponding AR. This is a MATLAB plot. So, in MATLAB AR is given as in a decibel unit. So, it is 20 log of amplitude ratio. So, if amplitude ratio is equal to 1, this decibel will be equal to 0. So, as long as this decibel value is positive, which means AR is greater than 1, the system is unstable. Here this decibel value is negative, so the system is stable. So, by you just naturally following from this thought experiment, what we have found is that using the body stability criteria, all we need is compute the corresponding crossover frequency and check the amplitude ratio. If it is greater than 1, system is unstable. Then we so the major assumption in the body's stability criteria is that these AR and phi are monotonous functions of frequency, and by that we mean as we keep on increasing omega from 0 to infinity, AR and phi both change in the same direction. And for a first order system, second order system, these normal transfer functions, this is indeed the case for most of the time, that AR and phi both will decrease like this figure. But in some cases this condition is not satisfied. So, what do we do? So, in that case we have to look at a more rigorous stability criteria, which is given by Nyquist, and that is why there are two diagrams, one is given for body and one for Nyquist. So, the Nyquist stability criteria also follows from the same thought experiment, however, it is more general compared to the body stability criteria, because what you see in the body's criteria or from the thought experiment is that in order to assess this stability, all we need is this signal should be sort of an inverted form of this. So, this inversion will happen when you have phase of minus pi, but the same thing will also happen at phase of minus 3 pi or minus twice n plus 1 pi. So, this Nyquist plot then looks at all these successive periodic values of frequency when these phases are multiples of 2n plus 1 pi, and then takes into consideration. So, if AR and phi are, if AR particularly is not a monotonous function of omega, then just satisfying this condition at minus pi is not sufficient. You have to look at the condition at every successive 2n plus 1 pi and ensure that all those ARs are also less than 1. So, in the Nyquist condition checks for amplitude ratio at phi is equal to minus pi, minus 3 pi, minus 5 pi and so on, and it says that all these should be less than 1 to ensure stability. So, in a way it incorporates body stability condition as well. And the way this stability condition is specified is using a Nyquist diagram. So it says that if you generate a Nyquist plot of a feedback system, and here you are actually computing the Nyquist response for negative frequencies as well. These are like that is not a real, this imaginary part which is minus infinity to 0 frequency. This is just to so that the Nyquist plot has a good shape. So what you do is you start with you draw the Nyquist plot for all these frequencies, and if it encircles point -10, then the closed loop system is unstable. So now what is so special about this point -10? When I say -10, this particular point -10 so -10 point, it says its amplitude ratio is 1 and the phase is minus pi, minus 3 pi and so on. So this represents all these points at which you are going to have this inversion of the signal, and so therefore if your Nyquist plot does not encircle this particular point, which means we will have a stable response. So here is a figure. So this particular figure shows this is the -10 point which is shown in red. So this particular Nyquist plot has a here the AR is not a monotonous function of omega, but you can see that -10 lies outside all this. So it is a stable system, whereas for this particular system this -10 point has been encircled using this circle. So it is going to be an unstable system. So this is the stability assessment in the frequency domain. So now if we want to get some results from this, what we would see that for a first order process, for simple first order process where G is Kp over tau s plus 1, so the maximum phi or the maximum phase lag we are going to get is pi by 2, because the phase is -90. So because of that the phase will never reach, the phase never reaches minus pi. So omega crossover does not exist. So as omega crossover does not exist, this first order simple first order process is always stable under P control, because when you have a P control, it is just going to add to the gain of the system. So the phase, it has no effect on the phase. Now when we look at the simple second order process, G is Kp over tau square s square plus twice zeta tau s plus 1. What you will see is that the maximum phase lag is pi, at which omega tends to infinity and AR tends to 0. So the omega crossover is actually an infinite frequency at which a second order system will give you phase of minus pi, and the corresponding AR is always 0. So even the second order system is also always stable under P control. So if you recall the example which I had shown you as a 3 tanks in series, because even if I would have considered single tank or 2 tanks in series without any delay, those systems will always be stable. So only when you have any system which is higher than second order without a delay, that will have some limitation in terms of the proportional controller gain. Any first or second order system will not have any finite omega crossover. But the case changes when you have any delay. So if you have but for first order plus dead time, so when you have Kp over tau s plus 1 e raised to minus TdS, the phase is minus tan inverse tau omega minus TD omega, and because of this term phi is equal to minus pi even for finite omega. So, omega crossover exists and is finite, and therefore, you also have finite Kc for stability. So, the moment you add any time delay, you are going to have some restriction from the stability limit. And note that we never approximated e raised to minus TdS. So, all the analysis which we have carried preserved the transfer function e raised to minus TdS. So, therefore, the stability analysis which we are going to get from this is going to be accurate, or it is going to be more accurate compared to a Laplace domain analysis. So, let us now complete this discussion by looking at the same tutorial problem of the blender. So, the blender problem. So, back to blender problem which had measurement delay. So, the Laplace domain analysis was domain approximate stability limit was Kc max equal to 8403. So, now let us look at what happens. So, here is the root locus diagram for that particular system. When there is no measurement delay, it is a simple flat line, it's all the poles move towards negative infinity, it is all stable because it is a first order process. When we have a measurement delay and we approximate it by a Paddy's approximation, you can see that the root locus diagram does cut the imaginary axis at these 2 points when the gain is 8403. So, that was the stability limit computed by using Laplace domain analysis. When we move to the Nyquist plot, and even though we consider any gain which is less than the stability limit, which in this case is 8400, you will see that it is encircling the point minus 10. So, the frequency domain analysis is correctly pointing out that this particular controller gain is unstable, and if we do the frequency domain analysis for this system, what we will analyze is that for frequency domain analysis, our GOL in that case is 8.33 10 raised to minus 4 over 3s plus 1. So, this is GP into GC is KC, GV is 1, and this is e raised to minus s. So, it is more or less like a first order plus dead time system. You can compute omega crossover such that phi is equal to minus pi. So, that omega crossover roughly comes out to be 1.5 radians per whatever is the time unit, and correspondingly if you equate and your AR is equal to 8.33 10 raised to minus 4 Kc over root of 1 plus 9 omega square. So, Kc max will be given by at stability limit phi is equal to minus pi, omega is equal to omega crossover, AR should be equal to 1. So, substituting it to be 1, you will get 1 plus 9 omega crossover square over 8.33 10 raised to minus 4, which comes out to be 6446. So, the correct stability limit in this case is 6446 as against what we have found using the Laplace domain analysis, which was 8403. So if we use any gain between 6446 and 8403, the Laplace domain analysis is going to say that the system is stable, but the frequency domain analysis is going to say that the system is unstable. And if you simulate the system, you will indeed find that the maximum stability limit is close to 6446. And here is the corresponding Nyquist plot. When you use any Kc which is less than 6000, you will see that this -10 point is outside this Nyquist plot, so the system is going to be stable. So we have now seen that how do we accurately capture the stability analysis of systems where there is significant dead time, and that we do by using a frequency domain analysis, which will be like capturing the amplitude ratio and phase as a function of omega, and then finding out typically the crossover frequency would suffice the job, and then you compute what is the amplitude ratio at that particular cross frequency. If it is less than 1, the system is stable, and if it is greater than 1, the system is going to be unstable. So that is about how do you assess the stability of feedback systems using frequency domain analysis. Thank you.